Section 1 still. And we are going to talk about symmetry. Now, there are three types of symmetry that we can have. We can have x-axis symmetry. There's the x-axis. We can have y-axis symmetry. And we can have origin symmetry. All right, so I haven't put any pictures of what that looks like yet. So x-axis symmetry. Symmetry is like, well, a heart has symmetry. Doesn't a heart have symmetry? Right here, it has symmetry, like the shape, yeah, the heart shape. It has symmetry right down the middle like that. Because you can fold it on, because now both sides on that line are equal to each other. And if I fold it in half, they match each other up. So x-axis symmetry would be a graph that if you fold along the x-axis, if you fold it right there, it's the same on both sides of that. So like, I don't know, this would be an example here, that kind of parabola like that would open left or right that you learned about in pre-calc in Algebra 2. A parabola that is, it has to be centered right on the x-axis, but that has x-axis symmetry. Okay, y-axis symmetry would be something similar. Let's make it a different graph, like a absolute value function that's a v that is centered right somewhere on the y-axis. Okay, that function has y-axis symmetry. And origin symmetry, the most typical equation that has origin symmetry is the line y equals x. But other things, you know, something like this function right here has origin symmetry. Origin symmetry is what I call rotation symmetry, and it's actually 180-degree rotation symmetry. So what that means is if I pick one point on the graph and then I rotate 180 degrees, I'm still on the graph, okay? And both points end up being the opposite sign. If I pick some point like this point here on this curve and I go halfway around the circle, I end up on another point right on that curve. And regardless, I could go the other way 180 degrees, still end up on the curve. So it's rotational symmetry is what the origin symmetry is. Now if you want to be able to find symmetry algebraically, which is very typically the way you want to do it if you don't always have a graphing calculator by your side, you can do it algebraically, or you could sketch a graph of this and see if there's symmetry. So actually we're going to use both of these methods, but I want to give some notes on, alright, so if it's x-axis symmetry, let's say I have a point A comma B, alright, I have to pick a general point. A comma B is a general point. And is A comma B on that curve right there? Okay. If it has x-axis symmetry, then the point, see how this point directly across the x-axis is also on there? Name that ordered pair for me. Very good. It is still over A, but instead of being up B, it's negative B. So this is A comma negative B. And if we're showing symmetry, we have to do it in general terms. When I say general terms, I mean A comma B. You can't just pick random actual ordered pairs to show symmetry. That is never correct to actually show it algebraically. Okay? You can do visual inspection if you've provided a graph and tell me the type of symmetry. Okay, but if you aren't graphing it, you have to do it algebraically and generally. And I'll give an example in just a minute. So that means for x-axis symmetry, A comma negative B is also on the graph. A negative B. Notice which one is the negative. It's the y. It's the opposite of the axis of symmetry. So here, if I have a point A comma B on the graph? And if there is y-axis symmetry, what point is also on the graph? Negative A comma B. So which one is the opposite sign here? X, the one that is not the axis of symmetry. Okay, now in the origin symmetry, if I have this point A comma B on the graph, I know that if I rotate 180 degrees, that point will also be on the graph. So what ordered pair would that be? Negative A, negative B. So that is a fact about each of these types of symmetries, and I can use that to do a test for each type of symmetry on any function I want. So I'm going to do an example here. I want to know y equals 2x cubed minus x has what symmetries? What symmetries? If any. Okay? You have to realize that many graphs have no symmetries. There are a lot of graphs that are not symmetric with the x-axis, y-axis, or origin. In fact, there are more that don't have symmetry than that do. Okay, just so you know. So some of your answers might be no symmetries. Alright, so I really don't want to graph this, but I can. I could graph this. I could make an xy table to graph this. Okay. And you can't see my xy table. Okay. So this has what symmetries, if any. So I am going to graph this just so you can visualize this, just so you can see that, hey, it is possible for me to graph this without a graphing calculator. I'm just going to throw in a whole bunch of numbers. Why? Because I know that this is an x cubed. I know it's an x cubed. And I know it's going to have curves. Cubed curves. All right? So I'm going to throw in numbers like -3, -2, -1, 0, 1, 2, and 3. And that is going to probably guarantee me that I get all the action that would ever happen in that graph. So I want to graph this. So all I need to do is plug these numbers in. I'm going to do it pretty fast. If I plug -3 in, -3 cubed is -27 times 2 is -54 minus a -3 is -51. Good. I don't want to graph that point, do you? Okay, so I'm not gonna. Is that a big deal? Okay, so now I put -2 in, and that's going to be -8 times 2 is -16 plus 2 is -14. I may not even want to graph that one. All right, that's fine. Plug -1 in. -1 cubed is -1 times 2 is -2 plus, okay, I think I can graph that one, right? -1, -1, -1. I like that point. When I put 0 in, I get 0. Yeah. Sure. Okay, when I put 1 in, I get what? 1. When I put 2 in, I get 14. Okay, so it kind of goes like way down here. So it looks kind of like that. That's my, well, actually it goes right through there, doesn't it? And then it should be, sorry, 1, 1, so it looks more like that. Okay. So based on this graph, what symmetries does this have?
Origin.
You think it has origin symmetry?
Yeah.
Okay. All right. Is that a way to tell me the symmetries?
Yeah.
Would I accept this for an answer?
Yeah.
Would I accept just this, origin?
Yeah.
And then you say, but Mrs. Kern, I graphed it on my graphing calculator and looked at it. Good for you. Tell me that you did that. Put the graph on the paper. Is the graph good? Is the graph good without any marks on here? No. This graph? No. No points. Not even if it's better. Not even if it's like this. That graph, not going to cut it. This graph and origin, that's good. Okay? All right, what if you could not figure that graph out? You got that -51 and you started crying. Okay? You can do it algebraically. I don't need to get a graphing calculator out at all. or make a graph. I can do it all algebraically. Some of you love algebra. Okay, you would rather be able to work it out and see it work. So here you can. Using the stuff we talked about with the negative a and negative b stuff up here, using that, I'm going to test for, I'm just going to start by testing for x-axis symmetry. And in x-axis symmetry, the ordered pair a comma negative b will also be on the graph. So I'm just going to try to give you a methodical way to do this. So we have our original equation, and what I'm going to do is, first of all, I'm going to change the x's and y's into a's and b's. Okay? So to test x-axis symmetry, it says if the point a comma b is on the graph, then the point a comma negative b is also on the graph. So first of all, I put a and b in, a in for x, b in for y. So b is going to equal 2a cubed minus a. That is a comma b on the graph. Now, this is where you got to listen. You got to use parentheses. Now I'm going to replace the a with a and the b with what? Negative b. Negative b goes in parentheses every time, no matter where you're putting it. So now I'm going to put negative b in for b and leave a the same. I'm testing for x-axis symmetry. If, in fact, this function has x-axis symmetry, then I will be able to simplify this, where I just put the negative in for b, so that it looks exactly like the one I started with. Simplify, okay? Now, can you simplify this at all? Okay, did we do it over here? No, we just want it to look like this. I'm not going to take out an a if there's no a taken out over here. This looks about as much like this as it's ever going to look. Okay? Can I get rid of that negative? I can? What's it going to do to this side though? It's going to switch it, so it's different than this. So is this thing going to have x-axis symmetry? No. No, it's not. I cannot manipulate this to make it look like this. Don't even try to do crazy stuff. Factoring. It's a waste of your time. There's nothing I can do. Anything I would do to get rid of this negative would switch this and not make it look like that. So this does not have x-axis symmetry. Okay, so now I move to y-axis symmetry. So now, don't I already have my equation, the a and the b substituted in? So now, for y-axis, I replace it with negative a comma b and see if it works the same. So basically, I shouldn't have crossed that out. This is the equation you want to keep for all the symmetries and compare it to. This is the one you need to make it look like every time you do the new replacement. So this time I'm going to replace b with b and a with negative a in parentheses. Now, can I do a little more manipulating with that? Yeah, I can. What's a negative cubed? A negative cubed is not a positive. It's a negative, so this would become negative 2a cubed. Minus a negative is plus. Does that, or will that ever look like that? No. No y-axis. So now I'm going to test for origin. Okay, so origin I'm going to replace with what? Negative a and negative b. So the b becomes negative, the a becomes negative, and now I see if I can make it look like the first one. Well, didn't I already simplify this part right here? Yeah, and that was negative 2a cubed plus a, and this is negative b. So what can I do here? How about I switch all the signs? Divide by a negative, take out a negative, it's all the same, right? And I get b equals 2a cubed minus a. Does that look exactly like that original one where I put the a and the b in first? So this does have origin symmetry, which is exactly what we thought. So yes, it does have origin symmetry.